This is section 2.9. It's on dot products. So the mathematical equation, maybe that's redundant, the equation for a dot product of two vectors, A and B, so A dot B is the sum of the products of the components. I don't know how to say that, but AX times BX plus AY times BY plus AZ times BZ. Alrighty, and notice there are no direction vectors over here on this side, so dot product of two numbers is going to be, or I'm sorry, the dot product of two vectors is going to be a number, or in other words, a scalar. So we'll look at some applications of the dot product, when to use it. Two applications. The first is the angle between two lines. And if you look at the figure over there, then you see that we have these lines R and B, or directions R and B. So we have, and we want to find the angle between them. This might be useful if we have an eye bolt connecting to a rope tied into the eye bolt, and the strength of the eye bolt decreases with the angle. So say we have an eye bolt like this. Its maximum strength is whenever the rope is pulling on it straight up, and it's weakest if you're pulling on it like that. And so we want to find the angle that the rope is pulling on the eye bolt at, so this angle theta. That's one possible application. So we might know the direction vector UR for the rope and UB for the beam, and we can use the dot product to find that angle between the two lines. And so we have this equation, cosine theta is equal to the dot product of the direction vectors. These have got to be direction vectors of magnitude 1, otherwise this equation won't hold. So in general, if we just have two vectors, A and B, that have magnitude, any given magnitude, then theta is equal to the inverse cosine of the dot product divided by the product of the magnitudes. So this just gives you U hat A and U hat B, so it's the same as this equation, but in general the magnitudes are not 1. So that's how we get the angle between the lines. So we are between two vectors. And then the second application is the component of a force parallel to a given direction. So we'll look at a different figure. So now we've got the vector A, and we have a direction U hat little a, or U little a. And we want to find the component of A in that direction. So if we know the angle theta already, we can just multiply the magnitude of A times cosine of theta, and that'll give us the component. But if we're given the vectors UA and A, and we don't know the angle theta, we can use the dot product. So the magnitude of the vector component A is the dot product of the vector A and this direction vector. So this one has to be a unit vector in order for this to be for this to work out, for this to be true. So here we've got a scalar. Remember, dot product of two vectors is going to give you just a number. So this isn't a vector. This is the same as referring to the figure where we know theta, the magnitude of A. So I just wrote that to stress the point that this is a scalar when you have the dot product of two vectors. It's just a number. All right, so we'll look at an example. So we've got a structure there, a little frame, points A, B, I guess A and B, and we have a force acting on the end of it, and we want to find the components of that force parallel to member AB, and also the component that is perpendicular to AB. So we need to get the position vector from A to B, and then the distance from A to B, and that will give us the direction vector, the direction from A to B. And we already have F in a vector, and then so we'll call it F AB. This magnitude is equal to the dot product of F and U hat AB. So R from A to B. Again, this is the difference between position vector B and position vector A. RB minus RA. And point B, the coordinates of it are 2, 6, and 3. So there's RB, and then RA is just 0, 0, 0. So R from A to B in this case, since A is at the origin, is just RB. So now we need the distance from A to B. And the magnitude of that position vector is just the square root of the sum of the squares. So 2 squared plus 6 squared plus 3 squared equals square root of 4 plus 36 plus 9 equals square root of 49, which is 7. And then so that'll give us the direction of from A to B. So that's just the vector, position vector from A to B divided by the distance from A to B. So that's UAB. And I'm not going to bother calculating that because I'll just write it in this step. And so we have F. We want to take the dot product of A and B. So this component of the force F that's parallel to line AB, or the direction of AB, is the dot product. And so that is equal to Fx times U hat, UABx. I erased the hat because that indicates a vector, and this is just a scalar value, so the x component. And I don't need parentheses, plus Fy UABy plus Fz UABz. Alright, so the x components of F and UAB, the y components of F and UAB, the z components of F and UAB. And again, this is not a vector. So we'll go ahead and perform that calculation, and F is in the y direction, so its x and z components are 0. So this goes to 0 and this goes to 0. And so we just have Fy, which is 300, and the y component of UAB, which is the y component of RAB, so 6, divided by the magnitude of RAB, which is 7. And there's the answer. So FAB is 300 times 6 over 7. So 6/7 of the force AB is, or I'm sorry, of the force F is directed along the line AB. And we also want to find a component perpendicular. So we'll call this FAB perpendicular. So drawing this figure, here's oh, that doesn't show up. So here's F, and here's FAB that we just calculated. So that's the component of F that's parallel to the line from A to B. And then what we're going to find now is the component of F that's perpendicular. So these two add up to F. So there's the vector, and showing that those are perpendicular, FAB. So we can use that relationship to get FAB. So we see that the vector F is equal to the sum of the vector FAB and vector FAB perpendicular. So hopefully that's clear from this figure. Vector F is the sum of vector FAB and the vector FAB perpendicular. So that's just decomposing it into rectangular components. So we have the magnitude of FAB, and now we want FAB perpendicular. All right. So FAB perpendicular is equal to F minus FAB. So F we already know, FAB we know its magnitude, but we need a vector. So we have here the direction from A to B. So this is equal to F minus magnitude FAB times the direction from A to B. And one more time, that's just substituting for the direction vector, we have the position vector divided by its magnitude, or the distance from A to B. All right, so we'll write down F, and that's just 400 in the J direction, minus now the component along AB. And so this is going to get kind of ugly, I guess. So we have the magnitude FAB, which is 300 times 6/7, and then we want the I, J, and K components of the direction vector, UAB. So we have times 2, which is the X component of the position vector from A to B, and then we divide that by the distance from A to B, which is 7. So there's the magnitude FAB, and we want to multiply that by the Y component of the direction from A to B. So Y component is 6 divided by 7. Magnitude FA to B, and now the direction is 3 over 7 times k. Got to remember the minus sign out here in front. So we've got negative 300 times 12/49 I. And then 400 minus this, so plus 100 minus and again, remembering that minus sign out front. So there is the vector of the force that's perpendicular to line AB. So that's this vector. And then to find the magnitude, we just take the sum of the square root of the sum of the squares. And I'm not going to bother doing that because these are big and long, and I don't have the decimal values, so that would get pretty big on the board. But the magnitude is just Alright, on that glorious note, I'll end this video. So now we see the uses for the dot product. And it's not something that we use terribly large amount of time, but it is useful to have in your toolbox.